Hello, dear students. Now we are going to discuss the next topic, which is block diagrams. So block diagrams are useful to visualize a complex system with many components. They are also useful to understand the flow and transformation of signals in a complex system and to find out the overall transfer function. So block diagram is a shorthand pictorial representation of system which depicts each functional component or subsystem or a part of system. Also, the flow of signal from one subsystem to another system. Block diagram provides a simple representation of complex systems, and also using these diagrams we can able to find out the overall transfer function. So there are certain components of block diagrams, typically 4 components. First component is block. For instance, G of S is a representative of one part or subsystem as a transfer function. Similarly, there are arrows. For example, U of S and Y of S are representatives of incoming and outgoing informations. Third important component is a summing point. For instance, U1 of S and U2 of S are two informations approaching to system. Here, the summing point is set as a subtractor. So the effective information coming out from subtractor is Y of S is equals to U1 of S minus U2 of S. Fourth component of block diagram is the take-up points or pick-up points. For example, this line is a 5-volt line which is represented as a U of S, and we want to take that information somewhere. So this is as good as a branching, or this is as good as connecting one wire and take that voltage information to another part of the system. Okay, the next part is the typical arrangements in block diagram construction. So the first arrangement is when blocks are in series or they are in cascade, then the overall transfer function is product of individual transfer function. For example, G1, G2 and G3 of S are connected in series. When U of S is excitation for the first block, so the effective information after first block is U of S into G1 of S. Then that information goes to G2 of S. So the information coming out after second block is U of S, G1 of S into G2 of S, and similarly it can end up with the final information. So final transfer function is given here. G of S is equals to Y of S over U of S, which is equals to G1 of S into G2 of S into G3 of S. Another arrangement is when blocks are connected in parallel. Same information is the excitation of these 3 blocks. So same information goes at a time to 3 blocks. So let's suppose Y1 of S, Y2 of S and Y3 of S are the outputs of individual blocks. So we will have the information like informations, and those informations are additive here. So finally the transfer function is in the form of Y of S upon U of S is equals to the addition of these 3 transfer functions. I hope you understood the simple mathematics. The third arrangement used in block diagrams is a feedback. Here it is a typical loop. G of S is a representative of system or a plant, Y of S is the output, H of S is the feedback transfer function, and this summing point is a error detector. So a typical loop in negative feedback. U of S is input. Now look at how the information is computed. To understand or to analyze this loop, you have to write 2 equations. First, estimate output. Y of S is given as G of S into E of S, which is the error information after error detector. In this square bracket, the equation for summing point is written, which is the difference between these two information, u of s minus this information is coming back, which is fed back to that error detector. So after further simplification, we will have two terms in which y of s is there, so we need to take this term in this side. So finally we will have y of s is into bracket 1 plus, look at this sign, 1 plus g of s h of s, and finally in the transfer function form is given as g of s upon 1 plus g of s h of s. Now this is a very important transfer function. At many of our further discussion we will use this transfer function. Now let us summarize, or let us understand how we got this transfer function. This transfer function is equals to plant transfer function upon 1 plus, in case of negative feedback this sign is plus, in plant transfer function into feedback transfer function. So I hope this is clear to you. If sign is positive or the loop is under positive feedback, then situation is different, that we will discuss later. So now come to the block diagram reduction. Suppose we have a complex block diagram, then how to reduce it into simplified block diagram. So block diagram reduction technique refers to the simplification of diagrams of complex system through certain rearrangement of blocks and certain simple computations, addition, subtraction, multiplication, etc. So this also enables easy calculation of overall transfer function. Using this, simplification is done using certain rules called as the rules of block diagram algebra, and they are very simple rules based on addition, subtraction of informations or blocks. All these rules are derived by the algebraic manipulation of equation representing the blocks. So let us discuss one by one these rules. So the first rule of block diagram reduction algebra is combining of blocks in series or they are in cascade. See the original diagram. G1 is receiving u as an input, and the next G2 is the block which is in cascade. So I think you can understand how the information comes out. Final information, so final outcome of information is u into G1 into G2. So if the blocks are in cascade, then we can do multiplication of blocks. So the equivalent diagram will look like this. So our concern is that the output should retain as it is. Okay, the next second rule is combining blocks when they are connected in parallel. For example, G1 and G2 are in parallel in the present arrangement. So individual outputs are u into G1, and for this block u into G2. So when we add, so here the sign should be positive. So the combined information is u into bracket G1 plus G2. So same thing is highlighted here. So when blocks are in parallel, then we can do addition in the effective block. Okay, the interesting part of block diagram reduction, when certain loop is there, either positive feedback or negative feedback. See, this is a typical feedback, typical loop in either in positive or negative feedback. Look at the sign. Plus is written first and my subtraction is written second. So for the next calculation we have to take care of this sequence. So finally, if you solve the effective information using appropriate treatment for first estimating output and again writing the equation for this summing point, we will get the effective information as u is input and See this is the uh, effective output of feedback loop, which is plant transfer function upon 1 minus or plus, in case of positive feedback minus, in case of negative feedback plus, into plant transfer function into feedback transfer function. See, the same thing is written here. So I hope this is clear. You may require some calculations here. So if you have some doubt, then do the individual calculations, and yeah, I hope you will get the equivalent prepared from this rule. Okay, the next is the interesting is interchanging of summing point. Suppose summing points are one after another. For example, A and B informations are approaching to first summing point. Let this is first summing point. So we will have, according to the signs provided here or the computations required, we will get the effective information, either summation, subtraction, or whatever is our demand. Let's suppose this is second summing point. So third information is approaching here. So we will have effective information as A plus or minus B plus or minus C. So interestingly, when you swap or when you interchange this, you have to keep track of output. So finally we want this outcome, that is A plus or minus C or plus or minus B. So when we, first information, second information, and third information. So when we rearrange or interchange, then this is first information, third information is either additive or subtracted at the first summing point, and then second information is coming. So effectively we will have the same outcome. So nothing has changed. This is the very simple rule, but very useful during the reduction of block diagrams. Okay, now look at this. When we want to move a summing point after block, now look at this. U1 is the information coming to summing point. Another information is considered as a U2. So you can understand how this addition or difference get computed by this summing point, and that effective input is given to the plant transfer function G. So we will have this. So this should get retained. Now if we simply move this summing point after this block, then we will not get the effective output. So because G will not coming on this path, and therefore the effective information will be different. So closely understand why this G is written here. So if we will not consider this block, then the information will be U2, and from this side we will have U1 plus U1 into G. So effectively we may have G U1 plus only U2. So G has to be adjusted here, and for that purpose we have to insert this block here to retain the required information. Okay, the sixth rule is moving summing point. So in the same way, to retain the original information here, it needs some calculations. So do some calculations so that you will understand why this 1 upon G is to be inserted here. So the required information is U1G plus or minus U2, and for that purpose this should be retained, and that's why this additional block is inserted here. Okay, so likewise moving a takeoff point after block needs this adjustment. Always you have to keep track of this the required information. Similarly, moving takeoff point ahead of a block, it needs again the compensation of this block. So a very interesting theory of reduction.